Hey guys, Mr. Smith here, and in this lesson, we're going to learn how to work with radicals. Now, you have been working with radicals already in your math careers. We're just going to take them kind of to the next level. When we're finished, we're going to revisit solving quadratic equations because then we'll be able to give exact values. You'll see what I mean in a coming lesson, but for now, we're going to work a bit with radicals. So let's get started. We're going to start with talking about types of numbers. Maybe you've heard this term and maybe you haven't heard this term before, but a rational number is a number that can be expressed as a ratio of two integers. So that's where it gets its name from. So a rational number could be something like, well, it could be like a fraction. So something like, 2/3. 2/3 is a rational number because it's one integer over another. You can have negative rational numbers too, like -4/5. But any integer, like a number like 4, that's a rational number too. And maybe you're wondering, well, how can it be a rational number? It's not one integer over another, but it is, right? Because 4 is the same as 4/1. 0, negative numbers. So those are all rational numbers. There's infinitely many of them. But some numbers can't be expressed as a ratio of two integers. These numbers are called irrational numbers. So you guys have experience working with irrational numbers. A very famous one is the number pi. It's like 3.14157.9, et cetera, et cetera. That number can't be written as an integer over another integer. And something we'll see today is things like the square root of 2, something like that. That can't be written as one number over another. And even something like the third root of 2 also. So all these types of roots, not every type of root, but those can't be written as one integer over another. So we have rational numbers, we have irrational numbers. Now, one type of irrational number is of the form root n, where n is not a perfect square. So as you can see, I had pi as an example, but then the other ones are like the root of 2, or like the root of a number like 7 or something, or cube roots. But a special type of irrational number is of the form root n, where n is not a perfect square. Such numbers are often referred to as radicals. So that's what a radical is. It's something like root 7 or root 11, something like that. We call that a radical. Now, can you think for a second while I let my dog out? She's bugging me right now. Why would root 9 and root 64 be examples of things that are not, why are they not irrational numbers? Okay, so have a little think on that. All right, just trying to teach a lesson. No big deal, right? I'm shooting YouTube videos at every possible second of every possible day. So to anyone at home in my kitchen right now. So why aren't they irrational numbers? Well, the root of 9 is exactly 3. And 3 is a rational number, right? Because 3 you can write as 3/1. Same thing with root 64. Root 64 is exactly 8, which is like 8/1. So that's a rational number too. These are perfect square numbers. Perfect square numbers. So the root of a perfect square number isn't irrational. It's actually rational because it gives you a whole number. Excuse me. And something that you guys should probably have in your math toolbox, taking this course, just a little numeracy piece, is you guys should probably know what the first, quite a few perfect square numbers are. It's like 1 squared is 1, 2 squared is 4, 3 squared is 9, 16, 25, 36. I mean, I could go on, maybe I will, 49, 64, 81, 100, 11 squared is 121, 12 squared is 144. I mean, I probably would expect most of you guys to know those guys that are perfect square numbers and be able to know their square roots right away. But those are all perfect square numbers. The root of any one of those is an integer. But the root of any other integer, like root of 2 or 3 or any in-between number, will be irrational. And today, we're going to just do a lot of work with radicals. We're going to simplify them, we're going to add them and subtract them, and we're going to multiply them as well. So to do that stuff, we are going to look at we're going to develop a rule. But instead of me just telling you the rule, I'd like you to do a little numerical investigation here. So I have, 2 columns, and the calculations look similar, but there is a difference. So in A, we're rooting each number and then multiplying the result. And then in B, you multiply the numbers together and then square root what you get. So I'll do a couple with you. So if we do column A, the root of 4 is 2 times the root of 4 is 2. 2 times 2 is 4. 4 times 4 is 16, and the root of 16 is 4. So those two worked out to be the same thing. The root of 36 is 6. 6 times 6 is 36. And 36 times 36, I definitely don't know that. Maybe I do. 36 times 36, 1,296. Yeah, I do. That was just purely memory. You teach math long enough, you're going to remember the stupid stuff you memorize. So it's the root of 1,296, which is going to give us 36, right? So I want you guys to do similar things with the remaining ones. So you can see that I have another one that's similar, root 5 and root 5. So maybe you want to keep those stored in your calculator. And then a couple other ones. So give it a try. And we'll check back in. If you want to pause the video and do that, check back in a moment or two, and we'll see how you guys did. So again, if you want to pause and unpause, that'd be great. I'm going to just do a couple here. So yeah, if you're ready to go, unpause and let's just finish it off. So the root of 5, is about 2.236, and the root of 5 is about 2.236. And if you multiply those guys together, you actually wind up getting 5 again. And 5 times 5 is 25. The root of 25 is 5. Those ones were all kind of obvious though, because obviously if you do 4 times 4, that's like 4 squared, and then rooting that, you just get 4 back again. Those were kind of obvious. It kind of made sense that those columns would match, but it's not entirely obvious for the remaining two. So what does the root of 12? So I'm just doing this purely in my calculator. The root of 12 times the root of 9. I got 10.39 about. And the root of 12 times 9, so that's the root of 108. What's the root of 108? You might be able to guess it. 10.39 about. Actually, I used 2 signs that mean approximately equal to, so that was approximately equal to 10.39. The dot above it also means approximately equal to, but you get about 10.39. And if you did the remaining 2, which I hope you did, I hope you paused and tried those on your own, you get about, I should write it there with a little dot, you get about 6.48. And then you also get the same thing here, about 6.48. They matched up. And then for the final one, you should have gotten about 16.52. And the actual numbers are relevant. What I hope you guys noticed is column A and column B always matched up. This motivates a rule for us that we can use all the time when working with radicals. And I think it's a pretty cool rule. So I'm going to get that on the next slide. So here's the conclusion. We have this rule. The root of some number times the root of another is the exact same as if you multiplied those 2 numbers together and then square rooted, which is not an obvious rule, but hopefully that you're convinced now. We just showed that it's true for a bunch of examples. And this is the rule. This is the fundamental rule we're going to use to simplify radicals and to work with them. And this is true for any positive bases A and B. So hopefully you're convinced. Let's do some things with it. Before we do, we're going to just talk about some terminology. So, in some situations, decimals are fine, right? So we've talked about how, like, the root of 3 it's a irrational number, approximately like 1.71 or so. There's my dog barking. I'm just going to let her in. If my wife needed that many pounds of something from the grocery store, like ground beef or something, I'm not going to go ask for, hey, can I have root 3 pounds of ground beef, please? Though that's silly. I'm going to say I need about 1.7 pounds of ground beef. So sometimes approximations are fine, but in other applications, especially since we're taking the university functions, in a lot of applications, we want the exact value. We want to be precise. We want to leave our answers in radical form, exact form. So we want to use radical form when an approximate answer is not good enough and we need an exact answer. We're going to leave things as radicals. So if we're going to start working with radicals, we need some terminology. So we call the number underneath the radical sign, we call it the radicand. So in this case, n is the radicand. It's the radicand of the radical. And we kind of already teased this already, but what values of the radicand will give irrational numbers? Or in other words, which values will give you rational numbers? If you want to pause and think about that, we already talked about it. I'll write it this way. Perfect square values of n give rational numbers. And numbers that aren't perfect squares are going to give you irrational numbers. All right. Other pieces of terminology. You guys want to get these down? An entire radical is a radical of the form root n, where n is greater than 0. So just below that, just some examples. Entire radicals like root 7, root of 20, root of 111. Those are all examples of entire radicals because it's just the root of some integer, and the integer has to be bigger than 0. A mixed radical is of the form some number times the root, or some whole integer value times a radical, where the radicand is bigger than 0. It has to be bigger than 0 because you can't root a negative number. And the value of a isn't 1 or negative 1. Because if it's 1 or negative 1, it's kind of like an entire radical. So an example or a few examples might be 2 root 3, 5 root 13, negative 4 root 2. Those are all examples of mixed radicals. And sometimes we can take entire radicals and simplify them. So just like you guys were taught with fractions, to make things in lowest terms, because it reduces the numbers and makes them smaller, maybe more manageable. In the same way, it's good to simplify entire radicals. And I'm going to do some examples with you guys showing you how to do that. This is a skill that we don't use every single day. We use it primarily when we're doing some solving of quadratic equations in this course. But later on through all your math courses, a lot of times where an answer involves a radical, it's going to be left as exact and it's going to be simplified. So I need to show that I need to teach you guys how to do that so you're well equipped. So here's 4 examples we're going to do. And I listed these earlier, but you're going to need to know your perfect square numbers for this. So 1, 4, 9, 16, 25, 36, 49, 64, 81, 100 is probably good enough. So the root of 50, I want to show you guys how we can write that in a simpler way with smaller numbers. And the key is this. We're going to use our rule from earlier. Do you guys remember this rule? The root of a times the root of b equals the root of a times b. But we can actually use that rule backwards. Look at our list of perfect square numbers. Do any of these numbers go into 50? Can you see one that goes into 50? I can. And at this stage in the game, in your math careers, it probably shouldn't take you a crazy amount of time to figure out which of these can go in. It's 25. 25 goes into 50. So watch what we can do, guys. I can write 50 as the root of 25 times 2. Now, how does that help us? Well, let's use our rule from earlier. Remember that rule? That rule says that the root of 25 times 2 is equal to the root of 25 times the root of 2. And what's the root of 25? Because 25 is a perfect square number. It's exactly 5. So we've taken an entire radical with a really big radicand, and we've simplified it to a mixed radical where the radicand is small. And that's good. Just like lowest terms is best with fractions, having a small radicand is ideal when working with radicals. We just got to get, kind of proficient doing that. As I said, it's not something that we have to use every day, but it's a useful skill that is necessary sometimes. You can always check your answers with these. If you do the root of 50, you're going to get something like 7.1 roughly. And if you do 5 times the root of 2, you're going to get the same value. So you can always check these. And moving forward, whenever you get an answer, say in your textbook, and the answer's like, the answer, you wind up getting the root of 50, your textbook will never show you root 50 as an answer. It will show you the simplified 5 root 2. So have to be able to convert these. Let's try the root of 27. Can you see a perfect square number that goes into 27? If you said 9, good job. So this is the root of, we can say this is the root of 9 times 3. 27 is 9 times 3. And then we use our rule from earlier to simplify. This is the root of 9 times the root of 3. And the root of 9 is 3. This is equal to, the root of 27 is exactly the same as 3 times the square root of 3. So pretty cool. And the mixed radical, just the numbers are smaller, easier to work with. We're going to do the root of 180 two ways. One is the quickest way, and the second is the maybe a less inefficient, like maybe a more a little bit of a more inefficient way to do it. But can you guys think of a perfect square number that goes into 180? So I'll pause and let you think about that for a second. I'm going to show you guys the most inefficient way first. You may have recognized that 4 goes into 180. So I can write 180 as the root of 4, and some quick calculator work. 180 equals 4 times 45. So this is equal to the root of 4 times the root of 45. That's equal to 2 root 45. Now that is correct, but is it as simple as possible? Or does another perfect square number go into 45? And another one does go into 45. 9 goes into 45. So I can write the root of 45 as the root of 9 times 5. So that's 2 times the root of 9 times the root of 5. I'm showing all kinds of steps here. In practice, you can shave off some steps if you're comfortable. This is equal to 2 times 3 times the root of 5. Finally, 6 times the root of 5. And root 5 can't be simplified anymore. Now, you can always, find a number that works, and just you might have to simplify twice. But it is always best if you can find the biggest one. So 4 and 9 actually weren't the biggest perfect squares that go into 180. Can you just scan down this list and see if you can see which one is the biggest? And if you notice 36, then good for you. The fastest way to do this one is to write 180 as 36 times 5. This simplifies to the root of 36 times the root of 5, which is equal to 6 root 5. And we get there just a bit quicker. Now, that's 4 examples in the books. I want to say something about showing work. For me, I would find it acceptable if a student showed me this. Root of 180 is the root of 36 times 5 equals 6 root 5. If you can just do that and recognize it's root 36 times the root of 5 and shave that step, that's fine. I may, once we do a few more examples, I may start to do that. But until you're comfortable, I always advise, like, show as many steps as you need to make sure that you are comfortable, okay? Cool. So now that we've learned how to simplify bigger entire radicals, once in a while, we might have to add or subtract radicals. And it's not so bad, actually. It's just like adding and subtracting like terms from what you guys learned in your grade 9 math course. So look at example A, 9 root 7 minus 3 root 7. Now, if you guys came to class today and I asked you the question, okay, where's my cursor? There it is. If I said, hey, what's 9x minus 3x? Everybody in here should be saying, okay, that's 6x, right? Just you subtract the numbers and you have like terms, so you keep the variable parts the same. It's the same thing with radicals. 9 root 7 minus 3 root 7, they're kind of like terms, and you would just subtract them, equals 6 root 7, and that's it. Like, it's that easy. If you have like radicals, you just add them like you would like terms. If you look at B, now right off the hop, B does not look like we can combine those together. And I really have to stress at this point, you cannot just mash together unlike radicals. And it's going to happen. Some of you guys are just going to want to take 4 root 3 minus the root of 27, and you're going to want to do like 4 minus 1 is 3, and 3 minus 27 is negative 24, which makes absolutely no sense because you can't read a negative number. No, you can't combine those. Just like, if you were in the grade 9 math course and your teacher had like 9x minus 4y, that can't be simplified anymore. Like, there's nothing you can do there. Those are unlike terms. You just got to stop. You got to leave it as 9x minus 4y, 2 separate terms. That's the case with radicals too. But can we make those into like radicals? Because we're looking at 27. 27 can be simplified, guys. Let's look at this one further. That's 4 root 3. 27 is equal to 9 times 3, where 9 is a perfect square. The root of 9 is 3. This is equal to 3 root 3. So I've shaved one step there where I went right from, I know the root of 9 is 3. So showed a lot of steps in the previous 4. If you're comfortable, you can shave off a step at this point. And now look, guys, those are like radicals. We can subtract them. 4 minus 3 is 1. And we're left with the square root of 3. So that's awesome. That initial kind of messy looking expression simplifies down to root 3. And as I mentioned earlier, you can check any of these. You can take your calculator and do 4 times root 3 and divide it by the root of, and subtract the root of 27. Then try doing the root of 3 and you will get the exact same answer. So an easy way to check. Let's do some more examples together. So let's look at C. We have 2 unlike radicals. We can't mash them together, but what if we simplified each one? Maybe we could. So let's look at 5 root 8 first. Is there a perfect square number that goes into 8? Yeah, 4. I can write that as 5 times the root of 4 times 2. And let's do the second one at the same time. So is there a perfect square number that goes into 18? Yeah, 9. I can write that as 9 times 2. Now, some of you will need to show more steps than others. I might show this intermediate step. So I know that's equal to 5 times 2 root 2, because the root of 4 is 2, plus 3 times the root of 9 is 3 root 2, and 5 times 2 is 10. I can just do that. So it's 10 root 2. 3 times 3 is 9. I can do that. 9 root 2. And now I can add these together. So that simplifies down to just one mixed radical, 19 root 2. That's pretty cool. Now, some of you, I would love everybody to show this step, breaking the numbers up into its product. But, I expect some of you guys to be comfortable enough to go right down to this last line, to do, for example, to do the root of 4 and then multiply that by 5 all in one step in your head. I think to me, that's reasonable. It's still showing some work, but it allows, if you get it, it allows for a little bit of flexibility. But you gotta just do what's comfortable for you. Show as many steps as you need to feel comfortable. All right, let's look at D. So D looks quite intimidating, but if we simplify each one of these, are there some like radicals that we can combine together? So I maybe would encourage you, maybe you want to pause the video and try D on your own. Try simplifying first, maybe unpause when you're ready to check something. But let's go for it, guys. So we have a half and 28. So I recognize that 4 goes into 28, 4 times 7, plus 63. I know that 9 goes into 63, 9 times 7. And minus 2/3, the root of 18. Well, 9 goes into that. That's 9 times 2. So let's do some simplifying now. The root of 4 is 2. That's 2 root 7. The root of 9 is 3. That's 3 root 7. And the root of 9 is 3. So this last one gives us 3 root 2. So right away I can see that I'll have 2 like radicals I can add, but I'll have one that I can't. So let's see how this finishes off. Let's simplify a bit. A half times 2 is just 1. So that's root 7 plus 3 root 7. And 2/3 of 3. So you can do 2 times 3 divided by 3. However you want to slice that, that gives you 2. And with the negative, that's negative 2 root 2. The only like terms, like radicals we can add are these two guys. 1 root 7 plus 3 root 7 is 4 root 7. And so this simplifies to 4 root 7 minus 2 root 2. In lowest terms, everything collected. Now, you might be asking, Mr. Smith, why are we doing this? What's the point? Are we ever going to come to a scenario where we have to simplify an expression like this? And I will tell you, the answer is no. We're not going to run across applications where we have to do this. So why do it? Well, we do these kind of questions to build up your skills, right? We do these kind of questions so that when you come back and have to do something like simplifying a radical, it's just automatic and lights out, right? So that's why we do them. And yeah, our goal in the 3U course is to prepare you for the 4U courses. Of course, we're going to see applications and do some useful stuff too. But at times, we're just building up skills. We're building up algebraic skills. So we do complicated looking algebra questions to build up your skills. So not everything we do is going to be when I'm going to use this in real life. If you're looking for something like that, the 3U course isn't kind of the place for that. This is the place where we're prepping you for kind of university, right? All right, little rant over. Let's continue. So we are not dividing radicals. As I was making this PowerPoint earlier, I put multiplying and dividing radicals. We're not going to be doing any dividing. We're going to be multiplying mixed radicals together. So just multiplying. So I'm going to show you how we can do that. And it's not so bad. It's the rules are pretty simple. You multiply the numbers, the whole numbers out front, and you multiply the radicands together. So here's our first example. 2 root 3 times 3 root 6. Guys, you just do 2 times 3, 6. and you do 3 times 6 inside the radicand, and we know that our rule, that's going to be 18. Now, that is correct, but is it as simplified as possible? The answer is no, because I can reduce 18. 18 is 9 times 2. I can square root 9. The root of 18, the root of 9 times 2 is equivalent to 3 times the root of 2. And 6 times 3 is 18. So fully simplified, that is equal to 18 root 2. Exactly. And again, you could double check that on a calculator. And that is a scenario that might pop up once in a while. Let's do some more involved ones, again, just with the intention of building up some skills. The distributive law holds when working with radicals. What's inside the bracket multiplied by what's outside. 2 times 4 is 8, and you leave the radicand alone. You multiply the numbers, you multiply the radicands. For the next term, we have 10. 2 times 5 is 10. And 3 times 3, that gives you the root of 9. My battery is low. I might want to plug in my PC. So I better do that so I don't mess up this video. Can you guys simplify any of those terms? Think about that while I get my cord. Please don't die, please don't die, please don't die. I have this thing too where if I plug in, sometimes if I plug in my power cord, I get the blue screen of death with my computer, which would mean I lose this video. So here we go. Bam. Okay. Phew. Crisis averted. Yeah, guys, just get used to it. These YouTube videos are going to be shot in every kind of room in my house and at school, and there's going to be hiccups. Did you notice that the root of 9 is just 3? That last term actually just simplifies to 30. Right? The root of 9 is 3. 3 times 10 is 30. Now, this is another example where some of you, maybe not all, but I bet many of you guys could probably just go right to that last line. You know that the root of 9 is 3. 3 times 10 is 30. But if you want to show intermediate steps, always a good idea. All right, 2 more, just building on the complexity, and then we'll do a little short application problem to wrap things up here. Check out this one. So we can use the double distributive law, like FOIL that you guys learned in grade 10, to multiply products like this too. So here we have 4 multiplications to make. So let's see what we get and ask if we can do any simplifying. So root 3 times 2. Well, that's just 2 root 3. There's no numbers to multiply or radicands to multiply. It's just 2 root 3. Root of 3 times negative root of 3 would give you negative, and then 3 times 3 is 9. So minus root 9, multiplying the radicands. And then we get 2 root 5. And the root of 5 times the root of 3 is just the root of 15 with a negative in front. And looking at our radicands, guys, we have root 3. Well, let's maybe do one little cleanup here. So 2 root 3 cannot be simplified. The root of 9, that can be, right? That's just 3, right? We just don't leave it as a radical. If it's a perfect square number, do the root, right? This is just equal to 3. 2 root 5, we can't simplify anymore. And is there a perfect square number that goes into 15? And the answer is no. So minus root 15. So this one's actually done. So here's an example where all these 4 terms are unlike. We can't combine them together. So don't try to. Excuse me. Last one here, guys. Doing good. Again, us math teachers, we're not trying to punish you or just make life hard for you. We're trying to equip you so that if we can do these, then when we really need them in an application problem or something important, we'll find that easy. So let's do it. So 2 root 2 times 2 root 2. So multiply the numbers, 4, multiply the radicands, 4. 2 root 2 times minus 3 root 3. Multiply the numbers. Minus 6. Multiply the radicands. 2 times 3 is 6. 3 root 3 times 2 root 2. Multiply the numbers. 6. The radicands. 3 times 2 is 6. And finally, 3 root 3 times negative 3 root 3. Multiply the numbers. Negative 9. Multiply the radicands. The root of 9. And now let's do some simplifying. So right off the bat, look, guys, negative 6 root 6, positive 6 root 6. Those are the same but opposite signs. They add to 0, right? 4 root 4, well, the root of 4 is 2. And then minus 9 root 9, well, the root of 9 is 3. So this is pretty cool. That big messy expression simplifies to 8 minus 27 minus 19. All that just worked out to minus 19. Can you believe it? It's crazy, but pretty cool in my opinion. I think working with radicals is kind of fun. It's fun learning. I think it's fun to learn new rules on how things work with each other in math. So that's great. So if you can do the level of C and D, like you're going to be well equipped to handle any situation with radicals from here all the way up to like calculus, let's say. All right, guys, I want to do one more thing. It's a really actual, pretty simple problem of finding an exact value, something where a problem where we want to know the exact value, an approximate answer won't do. So we're just going to solve a pretty quick problem. We're given the volume of a square base pyramid, and we know that the height is 9 centimeters. So for a pyramid, of course, everybody remembers from their grade 9 course how to calculate the volume of a pyramid. You take the area of the base times the height, and you divide that by 3, which is the same as multiplying by a third. But what are we given in this question? We're given the volume, 1,089, equals 1/3. We're trying to find the side length of the square base. So let's let the length of the square base be x. So let x be the length of the square base. So what's the area of that square base? Well, area is just of a square is just the side length squared. And the height is 9. So plugging everything in and do some simplifying. 1,089, 1/3 times 9 is just 3x squared. We can get the x squared by itself by dividing by 3. I might just rearrange sides. 1,089 divided by 3. Can I do that in my head? 363. Yep, still got it. And so exactly the base of this pyramid is the root of 363 centimeters. Now, my question for you guys is, can we simplify that any further? Is there a perfect square number that goes into 363? Now, there is. Can you find the biggest one? So maybe pause the video and maybe go way back to here. I've listed all the way up to 144. Can you find one? And pause when you're ready. So here we go, guys. If you notice that 121 goes into 363, good for you. This is the root of 121 times 3. And the root of 121 is 11. The length of the square base is exactly 11 root 3 centimeters. An exact answer. All right, guys, we did great. So now that we have learned how to simplify radicals, we're going to review how to solve quadratic equations. So maybe you remember the quadratic formula from your grade 10 math course, negative b plus or minus. Some of you guys may even know a song or some kind of rap or something, all over 2a. But calculating the x-intercepts or zeros or solving an equation using the quadratic formula requires you to do the square root of b squared minus 4ac. Now, once in a while, that gives you a whole number, but many times it won't. And if we want to have exact answers, we need to get used to the idea of using the quadratic formula and then simplifying what we get in that radicand using our new skills. So we're now fully equipped to do that. That's something we'll do in our next lesson. So until then, guys, hope you're staying well. Thanks for putting up with my life at home. That was definitely not the worst distraction that you're going to see this year, shooting videos from home. But yeah, I had fun shooting that one, guys. Hope you're staying well. Have a great day, and we'll see you soon.